Welcome to Pack Publishing's Oracle Coherence Quickstart video course. In this video, we're going to examine the contents of the Coherence Zip file, the general folder structure, and console utilities. To download Coherent's latest version, you can visit this web address. As you see, there are 3 different languages, and throughout this course we'll be using the Java version of Coherence. Before downloading the Coherence setup, you need to accept the OTN license agreement. After downloading and extracting the zip file, you should see 3 folders. Here, the bin folder includes the critical server and client batch files. The cache-server.sh or cache-server.cmd file starts a cache server. A cache server connects to the cluster and access data grid and holds data. Let's look at this now. As you can see, there are some parameter settings to manipulate Java programs. It configures some JVM parameters. Also, as you can see, you can configure the heap size from here. In the last part of this file, you can see that a Java program called starts the Coherence server with parameters that are defined above. The second batch file is the coherence.cmd file. It starts an interactive console for Coherence, and you can use it to run commands on the cache. This is similar to the cache server batch file, but it has a storage enabled variable. It specifies whether the console holds data or not. Generally, this console utility does not hold any data and just queries the cache, so this variable is set to false. As you see in the last part of this file, the cache factory class, which is in the com.tangosol.net package in the jar file, has been started. The datagram test.cmd file is used for the test and tune network performance in the cluster. You can set one of the servers in the cluster as the publisher and the other as the listener. Therefore, they communicate with each other. The package transfer rate can be observed using the utility, and the multicast test.cmd file is used for testing whether the multicast is enabled or not. You can test this by passing an IP address, multicast address, TTL, and delay parameters. The last file in the bin folder is the query.cmd file. This is similar to the Coherence CMD file, but it provides the functionality to query the cache through Coherence query language, which is an SQL-like query language. For example, you can run select name from customers where country equals Italy. The second folder on the zip file is the doc file. In the doc file, there is a documentation.html file. This redirects you to the Oracle Coherence online documentation. The index.html file in the API folder shows the Java docs for your current Coherence release. The other folder is the library folder. This folder includes many jar files that are being used for several enhanced requests. We'll look at these in later sections, but I'd like to explain just one of them here. Coherence Web is a library that provides HTTP session replication and high availability for web applications. In this video, we've learned about files that are presented in the Coherence Zip file and what they do. In the next video, we're going to see how to set up and start a Coherence cluster from the console. Now that you've got Coherence downloaded, it's time to get started. In this video, we'll see how to set up some Coherence parameters and start a cluster from the console. We'll also look at Coherence start log. Before getting started, you should have downloaded and extracted Oracle Coherence to your workspace. You'll need at least version 3.7.1. Okay, let's start. I'm using Windows 7 as the operating system, Coherence 3.7.1, and JRocket 1.6.37 64-bit as the Java development kit. You don't have to use JRocket, you can use any standard JVM. You could also use Oracle VirtualBox to set up an Oracle Enterprise Linux virtual machine on your usual Windows machine. If you want to experiment with Coherence installations, you could try some pre-built virtual machines for Enterprise Java development, downloaded from the Oracle VirtualBox main page. Now that we've downloaded and extracted Oracle Coherence, you'll be able to see some Coherence batch files under the bin folder. To start a Coherence server, we can use the cache server script file. Before running it, let's look over some parameters. We can set many JVM and Coherence parameters here. We'll just change the heap size parameter to 2 GB. We'll save it. After that, we'll start the Coherence cluster. In order to start the cluster, we must have 2 critical configuration files. One of them is the operational configuration file, which specifies cluster properties such as cluster name, cluster port, and TTL value. This file is called tangosol coherence override.xml. and the other one is the coherence cache config XML file, which provide the features of the cache, not the cluster. Cache properties include specifying the cache type, distributed, replicated, or near cache type. You can also set the cache size value, for example 1 GB cache size or 1 million cache entries. This also allows us to set the cache eviction policy, that is, looking out for least recently used or other parameters. If you don't specify these parameters explicitly, Oracle Coherence uses the default XML files from the coherence.sh file. In this example, I'm not covering these files in detail. We'll discuss them in detail later in the operational and cache configuration files section. Anyway, as you can see in the last line, we've started the cache server successfully. Let's have a look at Coherence's log. You can see the TCMP is bound to the machine's IP. This is because we did not explicitly set the cluster name. Coherence uses the default cluster name, that is, cluster. You can see a lot of information in this line. The JVM process ID and role of this server is Coherence server. You can also specify another role name in some configuration files. We are using Grid Edition as it is the most powerful one. The CPU and socket count of this machine is 4. The master member set displays all the membership information of the cluster, including the current server. This member clause gives information about the current server, ID, and other information. The oldest member clause contains information about the first server that joined the cluster ahead of all other members, while the actual member set gives information about all the members. Recycle millis keep track of when a member doesn't respond to a request for more than 120,000 milliseconds. Such a member becomes a recycled node. Recycle set specifies the members that were recycled. The services section specifies which services should be started. It is configured in the coherence cache config XML file within the coherence jar file because if we did not specify any XML file, Coherence uses the default one. We then come to the standard default cache server clause where we have a cluster with one member. If I add a new member to the cluster, they'll communicate with each other. To test it, start the cache server script in another console terminal. If we look at the master member set section on the new members log, you'll see the difference from our previous one. The ID value of this member set is 2, and in the actual member set section, we see 2 different numbers. If we look at the log of the first member after the new member joins the cluster, we see the first member recognizes the new member. If I shut down a member, the other member recognizes this, and according to the chosen cache type, Coherence will do whatever needs to be done. In this video, we've learned how to start a cluster and how to look at the Coherence log. You'll be able to start the cluster and understand what's going on there by looking at the output logs. In the next video, we're going to learn how to access the data grid from the console. Now that we know how to start a Coherence cluster and also understand the starting logs, in this video we're going to see how to access the data grid, in other words, the cache cluster, via the Coherence console. First of all, you should change the directory to the Coherence binary folder. Let's now take a look at the coherence.cmd file. As you can see, there is a variable storage enabled and it points to the dtangosol.coherence.distributed.local storage parameter of Coherence. If this parameter is false, as it is here, it means that this server, this JMV, does not hold any data. It just queries the cache. In the cache server, cache-server.cmd file, this local storage parameter should be set to true to hold data. Now, let's start the console. Note, cache servers are running in the background while I'm creating a new tab. This tool has an interactive command line, so we can call several things to perform cache operations. To get a list of commands, type in help. Firstly, let's create a cache. To do this, enter the cache clause and specify the cache name. We now have an on-the-fly cache. The size command gives us a number of elements in the cache. Because there are no entries in the cache, the size command gives us 0. So let's add an entry to the cache. The put command puts an entry record into the cache. It returns null. This is not a problem because we did not get anything. The 1 specifies the key, and turkey specifies the value. If I want to get the record, its key is 1, I can use the get command. The get command gets an entry from the cache and displays the value of the record. I would like to add 4 more entries. Then, if I want to list all the elements in the cache, I can use the list command. If I want to remove element 2, Germany, the remove command can be used. If I try to get element 2, I would get null value. The memory clause displays the free and max available memory of JVM. It can be advantageous to monitor the cache memory size to prevent the out-of-memory error before it happens. Let's try to put elements in bulk. To do this, the bulk put operation can be used. The first parameter sets the iteration size, the second one sets the memory size of each object, and the last one sets the key number of the first element. We put 50,000 more elements into the cache. Note that free memory locations should be decreased due to the added new objects. There are a few commands that can be used on the console. I'll list some of them in the upcoming sections. Finally, I'd like to show that even if one cache server is shut down or gets an error, we won't lose any data. As you can see, there are terminal tabs, 2 cache servers, and 1 Coherence console. Let me turn off one cache server. If you look at the Coherence console again, you'll see some logs about a cache server that's shut down, as well as transferred partition information. Let's query the size of the cache. It's 50,004, the same as before. In this video, we've learned how we can use the Coherence command line console to perform various operations on the cache. So you'll be able to do many operations in the cache, put, get, list, etc. via the console. In the next video, we'll learn how to start Coherence in Eclipse. In this video, we're going to discuss starting the Coherence cache server in Eclipse. Before getting started, I should mention that we use the Oracle Enterprise Pack for Eclipse. It provides many J2EE features and Coherence Facets as well, so we can use Coherence easily in our project. First of all, you'll need to create a Java project. I've named it Coherence First, and then click Next. To use Oracle Coherence in our Eclipse project, we should create a library and then add our Coherence jar file to this library. To do so, click on the Libraries tab and then the Add Library button. Then select User Library, click on Next, and then click on the User Libraries button. We've now created a new library. Let's use Coherence 371 for its name. Our library is ready, but it has no jar file. To add the coherence.jar file to the library, click on the Add Jars button and then select the coherence.jar file. The coherence.jar file is located under the library folder of Coherence Home. Click on OK, then on Finish, and our project is ready to use. Now that we have a Java project which is a Coherence library, we should configure the project in order to use Oracle Coherence features in Eclipse. Right-click on Properties and you will see the project facets to the left. Click on it, select Oracle Coherence line and click on the Further Configuration Available link. All items should be checked in this section. Then click on OK, Apply, and finally click on OK again. After all these operations, we can start the Coherence server. In order to do this, use the Run Configurations option. In the section to the left, double-click on Oracle Coherence. In the name field, enter Coherence First Run. It's important to consider which Java program is used as the main class. As we've seen earlier, there is a default cache-server class. We should use this class name here in order to run the cache server. Click on Apply, and then Run. As you can see, the cache server has been started. In this video, we've learned how to start the Oracle Coherence cache server in Eclipse. We're going to learn how to do some cache operations within Eclipse in the next video. In the previous video, we learned how to start a cache server in Eclipse. In this video, we're going to look at some cache operations within the Eclipse project. Before getting started, you should have downloaded and extracted the basic operations zip file and then import it into your workspace. In the readme.txt file, you'll find details on how you can extract it. Okay, let's get started. After you've extracted the project onto the Eclipse workspace, you'll see a basic operations project in the Projects section. Let's look over the files in this project. As you can see, there are 3 packages and a configuration folder. In this package, there is a customer class. This is our object, which will be stored in the cache. It has 7 fields and the fields getter and setter methods. It also has 2 constructors. One of them has no arguments and should be defined while using the POF serialization, which I'll explain in greater detail during subsequent sections. The other constructor method gets 7 parameters and sets the field's values. You can also see 2 methods. The readExternal method reads the customer object from a serialized form and can be used to fill any related class fields from the cache. The writeExternal method writes our customer object into the serialized form. These 2 methods must be implemented when we are using POF serialization. If we have another serialization method, we won't need these methods. This package contains 2 Java classes. The customer generator class generates a random customer object. It also provides the getCustomer method, which allows us to use a parameter to produce the customers list and return the list to the caller. The other class is the customer writer Java class. It produces customer objects and writes them into a file. You don't need to use these Java classes, but if you do want to change something and reproduce customers, you can definitely use this. If we look at this cache package, you'll see that there are 4 classes. The cache-start Java class starts a cache server. In order to do this, the getCache method of the cache factory class is used. Customers is the name of our cache and it should be defined in the coherence cache config.xml file. As we can see in the last part of this Java code, the program will expect a key to terminate this program. The second class, cache-insert, reads from a semicolon separated file and converts each line from the file into the Java object. Put this Java object with this key value into the cache. The third class, the cache-get-Java class, asks you which customer you want to retrieve from the cache. You can enter a number between 0 and the max cache size, and it will write the customer's information into the console. The last cache in this package is the cache-remove Java class. It asks you about which entry you want to remove, and we can type a number between 0 and the cache size. Configuration files make up the last part of this project. Under the config folder, we'll see 3 configuration files. The coherence cache config.xml file allows us to modify the cache configuration. The properties of the data grid that holds data are defined in the cache configuration. For example, size. How many elements or how much memory or objects can the cache hold? In our example, as you see in this part, the cache holds a maximum of 32 megabytes of data. If I change this to 64 megabytes, our cache can hold a maximum of 64 megabytes of data. If you want to change the cache size policy, for example, you don't want to limit the cache size in terms of byte, but rather limit the cache by number of elements. To do this, you could change the unit calculator parts attribute from binary to fixed and put a number here to limit the cache to. For example, I am typing 10,000. As a result, the cache will not hold more than 10,000 elements. The other configuration file is the pofconfig.xml file. This file shows which class should be serialized by using the POF or Portable Object Format serializer. As you can see, the customer class should be serialized with the POF serializer. The last file among the configuration files is the TangoSol coherence override.xml file. This file allows us to modify the server's configuration, not the cache. As you can see, only the cluster name parameter was set, while other parameters are read from the default configuration files that are inside the jar file. We will not use this configuration file in our project, but I'll demonstrate how you can use it. We have looked over the most important files associated with it. Now let's run the cache server. To run the cache-start Java class, right-click on it, select Run As, and then Run Configurations. As we did in the previous video, double-click on Oracle Coherence here, and then check the main class to see if it is correct or not. As you can see here, it's correct. We now have to define the cache configuration descriptor. To do this, click on the Coherence tab, click on this icon, and then on Source Path. We should choose the Coherence cache config XML file under the configuration folder, then click on Apply. In the other tab, you'll see many parameters. These are related server configurations. You can also specify a TangoSol coherence override.xml file in the Arguments tab by typing in this here. But instead, let's use the parameters in the Coherence tab. At the end of the line in this section, you'll see the configuration of the POF config file. You should specify the POF config.xml file path. To do this, click on Apply and then on Close. Paste it to the POF config.xml path configuration. Come back to the Coherence Parameters tab and paste this variable. Now you're ready to run this Java application. If you see this output, so far everything is okay. We now have a cache server, but it has no records. To add records, you should run the cache-insert Java class. Before running it, however, you should modify the customer.txt file's path. In order to run this, right-click on Run As and select Run Configurations. Let's duplicate this cache. Change the name to cache-insert and change the main class type to cache-insert. The other configurations can be left the same. The most important point is that the Coherence cache config.xml file for each server should contain a customer's cache information, because all servers should be able to access this customer's cache. If everything is okay, let's run this. If you see this output, there is no problem. We now have two cache servers that contain data. If you want to get an object from the cache, you should run the cache-get Java program. In order to run this, follow the same steps as we did before. Let's duplicate this cache again. Modify the name. Select a main class type. And finally, hit Apply and then Run. If you see this in the output, the cache-get program has run successfully. To retrieve a record from the cache, enter a value between 0 and 500. I entered 72, and it returned a record whose key value is 72. We have now added records into the cache and retrieved some of them. If you want to remove an entry from the cache, simply run the cache remove Java class. Let's duplicate this cache yet again. Modify the name, select the main class type, and finally, hit Apply and then Run. The application asks us which record we want to remove. Type in a number between 0 and 500, for example 42. As you see now, there are 499 records in the cache. If you try to remove an entry more than once, there is no change. In this video, we've learned about some cache operations within Eclipse. You'll now be able to perform run, put, get, remove, and some other cache operations easily. In the next video, we'll take a look at how to configure JMX in order to monitor what's going on in Coherence and how to use the JRocket mission control feature. So far, we created an Eclipse project and performed various tasks against the cache. In this video, we're going to look at how to configure JMX to monitor what's going on in Coherence and how to use the JRocket mission control feature. First of all, I should mention that all JMX configurations are disabled by default. To enable them, you need to configure the operational configuration file. In order to perform this, you have two options: edit the Tango Sol Coherence override XML file, or set some parameters in the Coherence run configurations within Eclipse. We will use the second option in order to speed up operations. Before getting started, you should download the JMX configuration projects.zip file and extract it into your workspace. After the project has been added to the workspace, we should configure the run operation. To create a new Coherence run configuration, right-click on the cache start configuration that was created before, and then right-click on Duplicate. We ought to modify some properties. First, change the name of the configurations to JMX cache start. After setting the name of this configuration, set the correct project name and the main class type. You'll need to click on the Coherence tab. As we've seen before, the Coherence tab contains 3 subtabs. We don't need to change anything in the General subtab. The JMX subtab is crucial to configure JMX. In the Management section, choose All and then check Enable Remote Management. You can also configure the RMI and HTTP configuration to overwrite the default values. The Refresh Configuration section provides the modifying and refreshing policy of Coherence and beans. After setting the relevant parameters, run the JMX cache start configuration. Let's now talk about JRocket mission control. To monitor these JMX monitoring enabled applications, run the JRocket mission control application, which monitors the running Java applications that use JRocket as the Java runtime environment. JRocket mission control is the JRMC executable, which is located under the bin folder of your JRocket mission control home folder. After starting the JRocket mission control application, you'll see the applications that use JRocket as a runtime environment on the left-hand side. Click on the cache start and then click on the Start console. Click on the mbeans icon. As you can see, the Coherence folder is at the top of the folder tree. If we set the management properties to none, we will not be able to see those. Under the Coherence folder, there are many attributes to monitor Oracle Coherence. In this video, we saw how to monitor Coherence mbeans via JMX. In the next video, we'll have a look at cache topologies. In section 1, we learn how to start, configure, and monitor Coherence cache applications. In this video, we'll take a look at what a replicated cache is and where it can be used. Before getting started, you ought to download the replicated cache operation zip file and extract it to your workspace, then import it to your Coherence project. After you've added it to your project in Eclipse, take a look at the cache configuration file in the config folder. As you can see under the cache mapping element, customers is used as the cache name and myReplicated schema is the schema name of this cache. If you take a look at myReplicated schema under the caching schema element, you'll see that it has a local schema as the backing map schema, and each server can hold 10,000 entries in its local cache. We know that each cache server contains the exact same data because the replicated schema is chosen. Before starting the cache server, let's check the run configurations. Duplicate the JMX cache server configuration. Name the configuration as replicated cache start. Correct the project name and correct the main class. Then, under the Coherence tab, check whether the cache server holds data or not. Also, check the JMX tab to see if the JMX management is enabled or not. If everything is OK, click on Apply and then on Run. The cache server has now been started. To run one more cache server, click on Replicated Cache Start again. So you should now have 2 cache servers with no data. In order to put entries into the cache, we should run the cache insert class. Before running it, add a new run configuration. Duplicate the replicated cache start configuration, and then correct the configuration name and the main class. Click on Apply and then on Run. Now we have 3 cache servers. The cache insert process adds entries into the cache, and then the cache size increases gradually. Let's check this via JRocket Mission Control. On the left-hand side, find the cache start class and start the console. In the mbeans tab under Coherence, Cache, myReplicated Service, you'll see 3 folders. Expand all of them and monitor the size attribute. Because we chose the replicated cache schema, the size attribute for each server is the same. We also add the size attribute to the dashboard in order to monitor it more easily. Click on Size, Visualize, Add Chart, and then OK. In Visualize, click on My Chart and select the size attribute again. Visualize, click on My Chart, OK. On the dashboard, over time, you'll see that there's no difference in the number of entries in all servers. If I shut down a cache server, the number of entries in the clustered cache should not change. Let's test this. Select a cache start and click on Terminate. Now, start the console again. Check the number of entries in the collateral cache. As you've seen, a replicated cache is useful and advantageous for fast data access because each server has no need to access the network in order to bring a record to the client. In the previous video, we learned how to start a replicated cache and where we can use it. In this video, we'll take a look at what a partition cache is and where it can be used. Partition cache is also known as distributed cache, and Oracle's documentation uses both of these names. Before getting started, you ought to download and extract the partitioned cache operation zip file to your workspace. After you've successfully imported the project in Eclipse, take a look at the cache configuration file. As seen under the cache mapping element, customers is used as the cache name, and my partition schema is the schema name of this cache. If you take a look at my partition schema under the caching schemas element, you'll notice that my partition schema has a backing map of local schema, and each server can hold 64 megabytes of data in their local cache. In the previous video, we used a replicated schema element under the caching schema, but in this example we are using the distributed cache clause under the caching schemas element. Before starting your cache server, check the run configurations. Duplicate the replicated cache start and update its name, project, and the main class type. Check if the correct project is being used and also whether JMX management is enabled or not. If everything looks alright, click on Apply and then click on Run. Once the cache server has started, you'll need to run one more cache server. Click on the partitioned cache start configuration, and you'll now have two cache servers without any data. To add objects into the cache, you ought to run the cache insert class. Before running the cache insert class, however, check its run configurations. Duplicate the partition cache start and correct its name and the main class. Then click on Apply. We need to disable storage in order to prevent this process from storing any data. Click on the disabled radio button in the local storage line and then click on Apply and Run. This project is similar to the replicated cache project we ran previously, but you'll see the difference while we are looking at JRocket mission control. We will expect all elements in the cache to be distributed almost equally among the cache servers with storage parameters enabled. For example, if the size of the clustered cache is 2,000 objects, each cache server holds approximately 1,000 objects. Let's check the attributes via JRocket mission control. On the left-hand side, find the cache start class, click on it and start the console. In the MBeans tab, under Coherence, Cache, My Partition Service, you'll see two folders. Expand both and monitor the size attributes. We've got 1059 and 1092. Select the partition schema. The size attributes don't need to be the same for each server. An algorithm takes care of the data distribution automatically, and all cache servers hold approximately the same number of records. For example, the first server holds 1074 objects, and the second holds 1104 objects. We can also add the size attribute to the dashboard in order to easily monitor its size. Select the size and click on Visualize. Add a chart and then click on OK. The partition cache is useful for holding much more data than a replicated cache in a clustered environment, because each server holds one partition of all the clustered data, and data in the clustered cache is the sum of data held by each server. While using the partitioned cache in some situations, we may have to access a network as the required object doesn't exist in the cache of a specific server. The clustered cache service receives the object from another cache server, and if the other cache server is running on a different machine, we may need network access. There is a critical question. What will happen if you shut down a cache server? As seen in this example, the clustered data is shared by the first and second server. Let's see what happens when we shut down one of the cached servers. This particular cache server holds 1,127 elements in its cache. Shut down this cache server, revert to JRocket console, and check the size attribute. As you can see, in the other cache server, there are 2,339 elements. It means that the second cache server holds backup data from the first cache server, and Coherence loads the backup data into the actual cache for the second server. In this video, we've learned how to use partitioned cache in our clustered environment. In the next video, we'll see how near cache works. In the previous video, we learned how to start a partitioned cache and looked at where you can use it as well as monitor it. In this video, we'll take a look at another cache topology. Before getting started, you ought to download the near cache operation zip file and extract it to your workspace and then import it. After you've successfully imported the project, take a look at the cache configuration file. Under the cache mapping elements, customers is used as the cache name, as we've used previously, and the schema name of this cache is myNearSchema. Look at myNearSchema under the caching schemas element. As you can see, myNearSchemas has two cache layers, the front and back caches. The front cache is a local cache that holds a maximum of 5 objects, whereas the back cache is a distributed cache which holds 100 objects. Another sub-element of near cache is invalidation strategy. It specifies the invalidating and refreshing policy. Let's try the near cache. Before starting, let's look at the cache insert getJava class under the cache package of the near cache project. We'll start this class as a cache server that can insert an object into the cache and retrieve an object from it. It asks what we want to do and performs the requested operation. Click on Run Configuration. Duplicate the partition cache start configuration. Then, update the name as near cache insert get1. Choose the appropriate project name and the main class. Check if JMX is enabled or not. Click on Apply, and then on Run. To create another cache server, back in Run Configurations, duplicate the previous configuration, and update the name to near cache insert get2. Then click on Apply and Run. We now have 2 cache servers and they are ready to perform an operation. Start JRocket Mission Control and check the 2 cache servers. On the left-hand side panel, click on one of the cache insert get classes and start the console. Under the Coherence folder, expand the cache subfolders. As you can see, there are 2 cache servers consisting of 2 front and 2 back cache. The values of all size attributes are 0. Get back to Eclipse and then choose the first cache server. To insert an object, type P and 1. This object is stored in the distributed back cache and not in the front cache. We can confirm this via JRocket Mission Control. We have just one object in the distributed back cache, and it can be stored on either the first or second cache server due to the distributed schema concept. In our example, we added an object to the first cache server, however it was stored on the second cache server. It could be stored in the first cache server too, but that's entirely up to Coherence's discretion. If you look at the front cache of the first cache server, the value of the size attribute is 0. The put operation is directly performed on the back cache when using the near cache topology. Back in Eclipse, take a look at the first cache server. Let's add records whose key values are 2 and 3. Back in JRocket Mission Control, you see that the size of the back cache is 2 plus 1. In Eclipse, choose the second cache server. To get records whose key values are 1 and 2, type in G and enter 1, and then type G again and enter 2. Let's check the coherence attributes in JRocket Mission Control. The total size of the back cache is 3, and as you can see, there are 2 records in the front cache of the second cache server because we retrieved records with key values 1 and 2 from the back cache into the front cache of the second server. If we retrieve the records with key values 1 and 2 again in the second cache, you'll see that the value of the number of hits for the front cache of the second server is 2. Let's try this example. Type in G and enter 1, then type G and enter 2. Then, back in JRocket Mission Control, click on Refresh. You can see here that the hit value of the front cache of the second cache server is 2. We have used the present option as the invalidation strategy, and let's check out how it works. For both cache servers, let's get the record whose key value is 3. Type in G and enter 3 in both cache servers, and you'll see the same record, Marie Atomic, as the result. As you can see, the object with a key value of 3 is present in the front cache of both cache servers. When we update this record from the first cache server by inserting a record with a key value of 3, the updated name and surname is Robert Nielsen. What will happen now when we request the object from the second cache server? Will Coherence display stale data that currently resides in the front cache of the second cache server, or will it get the new one from the back cache? Let's try out this example. Type in G and then enter 3. The name reflected is Robert Nielsen. As you can see, the object with a key value of 3 stored in the front cache of the second cache server is invalidated and refreshed automatically by the back cache. This happens because we have chosen present as the invalidation strategy. Near cache is a hybrid cache and combines the extreme performance of a replicated cache with the extreme scalability of a partitioned cache. In this video, we've seen how to use and monitor it. In the next video, we'll take a look at the implementing storage backing map concept. In the previous video, we've seen how the near cache concept works with sufficient examples. In this video, we'll see what the backing map schema's types are with a few examples. Before getting started, we ought to download the backing schema's operations zip file and extract it to your workspace. You'll then need to import the project. After you import the project, let's take a look at the external backing cache configuration XML file in the config folder. External schema has been used as a backing map schema, and in the external schema, the BDB store manager element has been used. It means that Berkeley DB.JE will be used to store all cached data. When the client performs a put operation, for example, this data will be stored in the Berkeley database and not in the JVM heap. Under the BDB store manager element, there are 2 parameters: the directory where files are stored and cache name. You should replace the values in these parameters depending on the folders you're using. The high units element specifies the maximum number of entries that can be stored in the external schema. Before we go ahead with the external schema example, click on Run Configurations, duplicate the near cache start, update the name to Backing Map External Schema Cache Start, and select the appropriate project and the main class. Then, in the Coherence tab, update the cache configuration file's name to external backing cache config.xml and select the local storage option. Click on Apply and then click on Run. In this example, the cache-start class is a little bit different from what we've seen before. It performs a get operation every second in case the cache is not empty. We know that retrieved objects will be stored outside the JVM heap. However, there are pointers in the heap directed towards Berkeley DB objects. Hence, the JVM heap will still be utilized. We want to keep the size of the JVM to a minimum, and that's why you'll need to use a garbage collector every second in this example. For the moment, we can use the system.gc as the garbage collector in our code. Cache start has been started, and to run the cache insert Java class, we'll need to click on Run Configuration again. Duplicate the previous one, update the configuration name and main class to cache insert external, and in the Coherence tab, disable the local storage option. Then click on Apply and Run. The cache insert external Java class in this project randomly generates between 20,000 and 50,000 objects and puts them into the cache. After cache insert external has started, let's check the cache attributes using JRocket Mission Control. On the left-hand side, click on Cache Start and start the console. In the mbeans tab, expand the Coherence folder and click on Customers. You can see that the size of the cache size is 350,000 objects. Click on Refresh. In the meantime, many items will be added. Check the value of the cache size again. You can see that the cache size increases gradually, but the cached objects are not stored in the JVM. In fact, they are stored in the Berkeley DB. Let's go back to the cache configuration file and examine the storage location specified in the directory element. In your operating system, go to that same path. At the path's location, you'll see the Berkeley DB files, and over a period of time, the number of files increases. When we get an item from the cache, it is fetched from these specific files. Let's open one of these files. Cached objects are stored in here, but as binary files, so it may not be apparent which objects are stored in the file. We can also monitor disk operations using the resource monitor in Windows 7. In disk activity, we can see that the JDB files are being accessed by Java programs. Let's now look at the second example of this project, the overflow schema. Take a look at the overflow backing cache schema.xml file in the config folder of the project. The overflow schema has two types of cache, similar to near cache. It has a front cache and a back cache. In our example, we have used the local cache as the front cache and the external cache, i.e. Berkeley DB, has been used as the back cache. It means that while the front cache tier, i.e. the local cache, can hold 100,000 objects, the subsequent data will be stored in the back tier, i.e. the Berkeley DB. You should replace this directory parameter with path locations as per the folders in your operating environment. Before we begin, you'll need to click on Run Configurations. Duplicate the backing map external schema cache start and update its name to backing map overflow schema cache start. Then select the appropriate main class, i.e. cache start overflow. Select the overflow backing cache configuration.xml file as the cache configuration file. Click on Apply and then Run. We currently have one cache server running. Let's have a look at the cache insert Java class. As mentioned earlier, there are two tier caches in the overflow schema, the front and the back cache. In the cache insert class, we will test the performance of the front and the back caches. In the cache configuration file, the local cache has been used as the front cache, and the external schema, i.e. BerkeleyDB, has been used as the back cache. Inserting objects into the front cache should take less time than inserting them into the back cache. Let's try this example now. Duplicate the overflow schema, update the configuration name to backing map overflow schema cache insert, disable cache client local storage option, click on apply and then run. The total put time for the front tier is about 5 seconds and is about 10 seconds for the back tier. As predicted, inserting items into the front cache takes less time than inserting them into the back cache, as front tier is a memory-based cache and back tier is a disk-based cache. In this video, we've learned what the backing map schema is all about. We also took a look at examples of the external schema and the overflow schema. In the next video, we'll take a look at read-through and refresh ahead caching. In the previous video, we saw what backing schemas are with some examples. In this video, we'll learn about the read-through and refresh ahead mechanisms that facilitate the retrieval of missing items from the base storage. Before we begin, you ought to download the readfromstorage.zip file, extract it to your workspace, and then import the extracted project files. After you've successfully imported the project, have a look at the read-through cache configuration XML file. Read-through is a basic method to retrieve missed items from the underlying data store, which could be a web service, database, or a file, to mention a few. To perform this operation, we should use a cache loader that either implements a cache loader interface or extends the abstract cache loader. In this example, we've used the customer loader Java class as the cache loader. Let's take a look at this class. The code in these examples is very basic. No design patterns were used to enhance it to make it more readable. You could easily improve the code's quality by using some design patterns. In the customer loader class, there is a load method, and Coherence will call it when a requested object is not present in the cache. Coherence waits for a response from the underlying data storage. As expected, this method works synchronously. In our example, we will use the H2 as the database. In the zip file that you've downloaded, there is a guide on how to install the H2 database and prepare customer data. After you've installed the H2 database and prepared the customer data, check the records in the customers table. You can view the database using a web browser. As you can see, there are 10 records in the table. Before starting the cache server, in the Run configuration window, duplicate the near cache insert get configuration and update the configuration name. Select the appropriate project and the main class. In the Coherence tab, select the cache configuration file, which in this case is the read-through cache configuration XML file. Then, click on Apply and Run. In the cache configuration file, we've set the expiration time for each entry to 30 seconds. The cache server has started. Type in 1 and take a look at the database logs. This log specifies that the object whose key value is 1 was requested at this time. After a few moments, let's type in 1 again and check the database logs. There are no more records because the object is already in our cache and has not expired. If, after 30 seconds, you type in 1 again, the object will be accessible and is retrieved from the database. Type in 1 and check the logs again. As you can see, there is one more record in the logs table. Next up, refresh ahead. Refresh ahead is similar to read-through. However, it provides an asynchronous method to retrieve items. In the refresh ahead cache config XML file, there is a refresh ahead factor parameter. The expiry delay parameter is set to 30 seconds. As you can see, if the same object is requested again 15 seconds after it was accessed, the new value is loaded from the database into the cache asynchronously and not synchronously. Oracle Coherence prevents the inconsistent response time by performing an asynchronous method. Before you try out this example, click on Run Configurations. Choose the previous one, update the configuration name, and choose the appropriate main class, and duplicate it. And choose the appropriate main class. Under Coherence, choose the appropriate cache config file. Then click on Apply and then Run. Get back to the database console, delete all logs by using the truncate query, and get back to Eclipse. After the cache server is started, there is no object. Type in 1 and check the database log, then start the timer. There is just one log. Type in 1 again in the cache server, and all we can see is the same log. But if we type in 1 again in the last 15 seconds according to the timer, there is one more record. It means that Coherence multiplies the expiry delay parameter with the refresh ahead factor parameter. If we send a request for the object in the cache in the last 15 seconds, Coherence starts an asynchronous job to refresh the object from the database. Check out the logs table to see this operation's log results. In this video, we've learned about the read-through and refresh ahead mechanisms which we can use to retrieve missing objects from the underlying data source in the cache. In the next video, we'll take a look at the write-through and write-behind methods to store cached objects in the underlying data storage. In the previous video, we've learned about the read-through and refresh ahead mechanisms that could retrieve items from underlying data storage. In this video, we'll learn about the write-through and write-behind methods by which we store Coherence objects in an underlying data storage. Before getting started, you ought to download and extract the write into storage zip file and import the project into your workspace. Let's take a look at the write-through cache config.xml file. This file is very similar to the read-through cache config.xml file which we have seen in the previous video. The difference is in the cache store class name. In this project, we use the customer store Java class for the cache store. Let's look at the customer store Java class. The customer store Java class implements the cache store interface. This class is similar to the customer loader class that you saw in the previous video. This class has more methods, however, the store method for example. The load method in this class is used to load missed data from the underlying data storage, and the store method is executed when an object in Coherence is updated or a new object is inserted into the cache. The write-through method works synchronously, just like the read-through method. Let's look at an example. Click on Run Configurations, duplicate read-through cache get, update the configuration name, and select the appropriate project name and the main class. In the Coherence tab, select the correct cache configuration XML file, then click on Apply and then on Run. Let's insert an object whose key value is 11 directly into the customer's table in the database. Before this, let's check the database. We can see 10 records. Now let's type in P and enter 11. As you can see, the object with a key value of 11 is inserted into the table. As mentioned before, this method works synchronously, which means that the client should wait for the database operation to be completed. In the write-behind method, Coherence does not need to wait. It puts the object into the queue, and a background thread writes queue objects into the database table asynchronously. Let's look at the write-behind cache config XML file. You can use the write delay parameter to set a minimum duration time value in order to force records to stay in the queue. In this example, we set the value to 30 seconds. After we put the object into the cache, the object is inserted into the queue and not the database. After an interval of 30 seconds, the background thread writes this object into the database. Before we look at an example, click on Run Configurations. Duplicate the previous configuration name and update the configuration name and main class. In the Coherence tab, select the appropriate cache config XML file, click on Apply and then on Run. After the cache server has started, type in P and enter 12. At the same time, click on the timer and check the customer's table log in the database. The object whose key value is 12 has not been written into the database because just 15 seconds have passed. However, after an interval of 30 seconds, you can see the customer object that was present in the queue written into the database table. Check the table logs, and there it is. In this video, we've learned how to store a cached object in underlying data storage. We use two methods to perform this operation: write through and write behind. In the next video, we'll take a look at serialization and POF configuration. In the previous section, we've learned about cache topologies such as replicated, partitioned, near cache, and backing schemas. We also got to know how to communicate with the underlying data store while using the get and put operations by using read-write backing map schema. In this section, we'll take a look at serialization methods to use objects across a network. Java.io.serializable, it is the simplest but is the worst in terms of performance. Java.io.externalizable, it is better than serializable because it reduces CPU overhead, however it is not the best option. The third one, com.tangosol.io.externalizable lite, it is better than the previous one because of reduced memory usage. The last one, com.tangosol.io.pof.pof serializer, it is the most recommended serialization method in Oracle Coherence. We've used portable object format serialization so far in our examples, and in this section we'll learn about it in depth. Before beginning with the examples, you should download the serializer.zip file and extract it into your workspace. After extracting and importing the unzipped file into your workspace, let's take a look at POF config XML file in the config folder of your project. Please note, there is one more method to use the portable object format. You need to call the POF register classes in the Java code. However, the XML type configuration is preferable as it is more flexible. The classes that will be used as coherence objects should be defined under the user type list element. Type ID should be more than 0, but between 0 and 1000. As you can see, a coherence internal object has already been defined here. Hence, in this example, type ID starts with at least 1001. In the class name element, we must define the class name with package name. Now that we had a look at the POF config.xml file, let's look at the customer class. Our customer class has implemented the portable object interface, and this interface forces us to implement the read external and write external methods. In both examples, we are using index values. I have specified them in uppercase. For example, ID is equal to 0, first name is equal to 1, and so on. Using the order of the index, values should be the same for both methods. For example, in the read external method, the ID index variable is 0. Hence, in the write external method, the index whose value is 0 should be used first, otherwise it will throw an exception. In the read external method, the reader object is read from the cached object in Coherence and then returned to the client. The read string, read initiate, and read object array methods have been used, and there are also some other methods. A similar method is the write external method. It writes the customer object into the cache by using the write string, write integer, and write object array methods of the writer object. Let's look at an example. Before we start the process, click on Run Configurations. Duplicate any one of them and update the main configuration name. Choose the appropriate project name and choose the relevant main class. Then check the appropriate Coherence config XML file source and then click on Apply and then click on Run. After the cache server has started, type in P and then enter 11 as the value. As you can see, the writeExternal method was called in this case. Now type in G and then enter 11 as the value. In this scenario, the readExternal method has been called. In this video, we had a look at the serialization methods and how the concept of portable object format works. In the next video, we'll have a look at the preloading cache methods. In the previous video, we had a look at the various serialization methods used in Coherence. We also had a look at the concept of portable object format in detail. In this video, we'll take a look at how to load the Coherence cache after the cache server starts. Before testing the application, you should download the preloading.zip file, extract it, and then import it to your workspace. In the data package, open the cache preloader.java class. I've already installed a H2 database, and we will fetch the records from the customer table in the Coherence cache. We'll start 2 cache servers, and each of these servers will fetch data according to the customer ID. The first cache server will get the records whose keys values are odd, and the second cache server will get records whose key values are even. How do we define which cache server will store odd values and which server will hold even values? The memberSet parameter defines a cluster's members. In this example, the memberSet.size will return the value 2, as we'll have 2 cache servers, and the member variable holds the cache server's information, such as the member ID and the machine name. This method is the simplest way to use the cache member ID and any other member information in the Java code. However, it can be prone to error. For example, if one of the cache server's status is storage disabled, our code will not work properly. Please note, you can use the Coherence API to perform various operations for fetching member and cluster information in the Java code. In this example, this member ID and the total number of servers is displayed using the printin Java command. It's imperative to know these 2 values, as we can use them to easily distribute database records across the cache servers. In the select statement, we use the mod method to direct the member to fetch one part of the data. While executing the query, we'll insert the database record into the buffer with each iteration. Note that we do not write the database record into the cache. If we call the put method for each step, there will be some significant overhead for network and memory I/O, especially in the case of replicated and distributed caches. Instead, you could use the put_all method to perform a bulk load scenario. To start the preloader, create a run configuration that runs the cache preloader class. The procedure is the same as shown previously, and in this case, there will be 2 preloaders. We must start the 2 cache preloaders at approximately the same time. This is because the first server might exit from the cluster in case the second server joins the cluster after a certain amount of time lapses. In this example, we have 2 cache preloader processes and they load data from our database into the cache. As you can see, this cache server's ID is 2. Remember that we have 2 cache servers in this example, and this one loads half the data, 6 objects in this case. As you can see in the other console, this cache server's ID is 1. In this video, we have learned how to populate cache data efficiently from underlying data storage in parallel. In the next video, we'll take a look at querying a data grid. In the previous video, we learned about loading the cache before starting cache operations. In this video, we'll take a look at how to query the data grid using filters, indexes, and aggregators. Before we begin, you should have downloaded the queryingthedataGrid.zip file, extracted it, and then import it to your workspace. In the cache Java package, there are 5 classes, and we have already created run configurations for these 5 classes using the same procedure as in the previous sections. The most important part of the run configuration is that the storage option must be enabled for all run configurations. Initially, let's have a look at the cache query filter class. We'll begin by defining some variables and fill the cache. After that, we'll add 3 countries elements into the country set and then create a filter. The filter is a Java class used to fetch the search data from the cache. We can use both predefined filters and custom filters. In this example, we'll use 3 types of built-in filters. The reflection extractor class is a core class used for extracting fields from the object. If you do not use reflection extractor, it is automatically chosen by default. Note that you can also define custom extractors in here. The getID method will be called and a returned value will be compared with 1000. As you can see, these 2 parameters were used in greater filter and in this case we're looking for customers whose ID is more than 1000. The other filter is InFilter. The getCountry method will be called, and Coherence will look at the customer's country attribute present in the country set that had been defined earlier. At the top we can see the filter in the code, and it combines the two conditions, greater filter and InFilter. In this case, we'll have a look at customers whose ID value is more than 1000 and country value is Italy, Japan, or England as defined in the code. After the filter has been defined, we define the filtered data set. The entrySet method in this example gets one argument, and this filters the argument defined earlier. This method returns the filtered objects to the filtered data set. After we have the filtered data set, we print out the filtered data size, and the program requests that the number of elements be printed. We can then easily print out the objects that are filtered using the iterator. Let's run this program now. In this case, we can see a list of 3,298 customers returned by the query. We'll print out details for just 10 customers by typing in 10. Once you've got your data, your next step would probably be sorting, which is similar to the previous process. However, while invoking the entrySet method, we'll add one more argument as the comparator. In this example, we set this argument to null, as a result of which the compareTo method is called in the customer object. As you may know, this method was defined on the implementation of the comparable interface. The customer object has a compareTo method. When we invoke the entrySet method, the data is initially filtered and then returned to a sorted clients list by citizen number. Let's try this example to see how it works. As you can see, the filtered data is sorted according to citizen number. Our next example is specific to limiting where we fetch data from the cache. This is similar to the sorting example. In this case, while forming the filter, we'll put the limit filter clause higher up in the code. The filter clause in the previous example is now the first argument of the limit filter, and the second argument is regarding the number of entries which will be fetched. In this example, we will initially fetch just the top 10 records and print them. After that, we'll use the nextPage method of the filter class, and it will set the filter for fetching data from the first 10 to 20 records. In this way, we run the query against the cache and it returns records between 10 to 20. Also, at the bottom, as you can see, we can set the page number. Setting the page number to 6 means the records from 60 to 70 will be fetched. Let's now try the limiting feature. As you can see, the entries are printed page by page. Paging methods are useful, especially for websites where you want to display reports that contain large amounts of user data without any latency. Our next example is about indexes. As you know, we can use the index feature in relational databases to improve query performance, and indexes can also improve query performance of the Coherence cache. Information about indexed objects are stored in another location in the Java heap, and if a client wants to query an indexed field, then just those specific objects will be retrieved. Else, by default, all items are stored in the cache in a deserialized manner. This increases CPU, memory, and also network overhead. In this example, we'll compare the performance of our query with and without an index. Initially, we'll create the set and filter. For a filter, we could use InFilter. We'll be looking for records whose country names are Japan, Italy, or England. We'll use the addIndex method to add an index, which creates an index by using the country field of the object. Let's look at the example and start the test. The cache is being loaded, and as you'll see, 5,000 objects are being loaded into the cache. We then run our query against the cache. If you observe the result, you'll see that it takes 740 milliseconds while using the index compared to 3,200 milliseconds without using an index. Hence, indexes can improve performance when we invoke a filtered query against the cache. Remember that indexes are stored in the Java heap, so you should configure the heap size correctly when using indexes. Our last example is about aggregation. Sometimes you may want to retrieve the aggregated value of a field for a specific partition. For example, you may want to get the average age of a customer in Japan. Hence, you'll just need one value that's an average. Coherence provides an aggregate method to do this easily, and you can run this type of query directly on the cache. You can see the aggregate method used in this example with two arguments. The first argument is the filter, and the second argument is the aggregate function. The filter was defined earlier, and it's the same as what you've seen in the previous example. Instead of a filter, a key collection could also be used here. Coherence provides many inbuilt aggregate functions, and we can also define custom aggregate functions, but in this example, we'll just use 4 of the inbuilt aggregate functions. Long max gives us a maximum long value of age fields in the filtered customer dataset. Long min returns the minimum long value of age fields in the filtered customer dataset. Double average returns the average value of the age fields. And finally, distinct values gives us the distinct countries in the filtered customer dataset, and it should be Italy or Japan or England because we filter data according to these attributes. Let's run this example to see how it works. As you can see in the results, 10,000 objects and some aggregated values were written in the cache. How it functions is quite evident. In this video, we've learned how to query Coherence cache data using filters, indexes, and aggregators. In the next section, we'll learn about entry processors. In the previous video, we've learned how to query a data grid using indexes, filters, and aggregators. In this video, we'll learn what an entry processor is. An entry processor is used to process cached objects in the storage node where the entry is located instead of bringing them to the client. Before we get started, you should download the entry processor.zip file and extract the unzipped file into your workspace. After importing the project, open the cache without entry processor class. In the first example, we won't use an entry processor when incrementing customer age. Initially, we will retrieve customers whose age will then be incremented by 1 into the client. We will then return them to the clustered cache. In the cache without entry processor class in the update part, we can see that the updated object has been locked and then brought into the client for processing. And then the age value is incremented by 1 and then put back into the cache. Let's run this example. Before running it, I've already prepared 2 run configurations for the cache without entry processor and cache with entry processor classes. You ought to prepare these configurations as well. The process is similar to what we followed in previous examples. Let's run this example. As you may have expected, this method has some performance issues. For example, we ideally ought to acquire a lock while getting items to and from the client. It would be optimal if we have a chance to process the cache data without fetching them in the first place. With entry processors, we don't need to fetch the object into the client to process it. The processing operation is executed on the storage node. Open the cache with entry processor class. In the update part, you'll see just one line of code. The invoke method is called, and this method delegates the modify operation to its submethods. This invoke method has 2 arguments. 1. In the first argument, the objects will be modified. In this example, we modify just one item, so we just type a variable that equals to 5. In the second argument, we have the processor object. Cache customer process is an entry processor that implements abstract processor, and it forces us to implement the process method. In the process method, we get the customer object, which is then updated locally by calling the setValue method. In this particular example, the customer class has an increment age method that increments the age field by 1. Before running the example, check the POF config XML file. You need to add a new cache customer processor object that's serialized so it should be added into the pof config.xml file in order to be transferable between nodes. Let's try this example now. Note that you can also define inbuilt entry processors such as conditional processor, number incrementer, or number multiplier here. But in this example, we defined a specific processor. In this example, while observing the results, it is quite evident that invoke and invoke-all methods are useful while modifying data because we don't need to fetch data into the client in order to modify it. Instead, execution was performed in the storage node that contains the object. In this video, we have learned about the entry processor. In the next video, we'll learn about cache listeners. In the previous video, we learned how we can invoke the entry processor to modify objects without bringing them into the client. In this video, we'll learn how the nodes and cache servers recognize object changes in the cache. Before testing the feature, you should download the event listener.zip file, extract, and import it into your workspace. After importing the project, you should prepare the run configurations for 3 classes that are in the cache Java package: listen all, listen filter, and listen light events. After successfully creating the run configurations, let's have a look at the listen all Java class. We use the add map listener method to add an event listener to our cache. This method has one argument, which is the user-defined event listener, which implements the map listener interface. The map listener interface presents us with the following 3 methods to recognize cache events. The entry deleted method is called when an object is removed from the cache, and we use the delete object method to execute various operations. The entry updated method is called when an object is replaced with a new one. It takes one argument, and we can use both old and new objects in this method. Last but not least is the entry inserted method. It also takes one argument, which is the object that is inserted. Let's start the 2 instances of the listen all class. You'll notice that the second server recognizes insert, delete, or update operations, which are performed by the first server. On the first server in this case, we will add one object. Let's have a look at the second server now. The second server recognizes the object that is added by the first server. We then perform one more operation. Insert an object into the second server, and you'll notice that the first server recognizes the object. The second example is about light events. In the previous example, we saw that you can access both the old and new objects information in the event listener method. If you are sure about the change that you are looking for, but not the object itself, you can use light events. With the light events feature, however, you cannot access objects. Let's see this in an example. In the listen light events Java class, the add map listener method gets 3 arguments. The first argument is the same as that of the previous one. The second argument is that of the filter class, which we set as null in this example. It means that all events will be listened to. The third argument specifies whether the light events feature is enabled or not. Let's run 2 instances of the light events class. In the customer event listener class, you can see that the customer IDs are printed in all the 3 methods. But if we use light events, we would not be able to use the object value. Thus, we will get an exception if we perform a cache operation. Let's see how this works. Type in P and then 10. Since we cannot access the object's value here, we get an exception that is quite evident from the result on the screen. The third example is about listening to the filtered data changes instead of all the changes in the data. In this example, for the listener filter method, initially we define a filter variable. Then we use this filter variable as the second argument of a map event listener object. Now, when we call the add map listener method, we put the map event listener object into the second argument. The map event.all feature specifies a pre-filter. It means that we initially observe all the events and then perform the other filters. Alternatively, you could also use the delete, insert, and update pre-filters. In fact, we will be observing changes that will be performed for a customer whose ID value is 100. Let's try this example out. Start 2 instances of the listen filter example. Now type in P and then 10. From the result, it is quite evident that the second server doesn't recognize any changes, as the customer ID is not 100. Now type in P and then 100, and we can see that in this case, the second server expectedly recognizes changes as the customer ID is 100. Finally, let's take a look at the process of adding a custom filter that listens for specific events. In the update filter class, we define the rule in the evaluate method, as you can see here. You'll also need to implement the serialization method and a portable object interface as well. Along with that, we'll have to configure the POF config.xml file to use a custom filter across network nodes, as you can see here. In this video, we learn how to listen to all events or filtered events. We have also learned the concept of light events. In the next video, we'll take a look at using map triggers. In the previous video, we took a look at how the event listener works with a few examples. In this section, we'll see what a map trigger is. Map triggers are invoked just before cache operations, unlike event listeners which are executed just after the cache operations asynchronously. Map triggers are useful for operations such as validating or modifying a pending value, to mention a few. Before testing the application, you should download the maptriggers.zip file and extract it into your workspace. After importing, let's take a look at the cache-insert-get-trigger Java class. The most important part is the line that we are using for the addMapListener method. This is similar to the one used in the previous section, but in this case we build a mapTriggerListener object and then insert the object as an argument. The mapTriggerListener constructor gets one argument, which is the user-defined trigger, that is, the customer trigger. We had defined our rule in this Java class. Let's have a look at this. We have defined our rule in the process method of the customer trigger class in this example, and this process method is invoked just before all cache operations. If the customer ID is higher than 100, we will get an exception. Let's see how it works. I have already prepared a run configuration for the cache-insert-get-trigger class and begun 2 instances for the same. As per the code, if we put a customer whose ID value is higher than 100, this object will not be added to the cache and will get an exception. Initially, type in P and then 20. This object gets inserted in the cache as the customer ID is less than 100. Type in G and then 20 to retrieve it. It works just fine. When we type P and then 500, we get an exception as expected. When we type in G and 500 to retrieve it, we get an error message that says the ID is invalid as the object has not been inserted into the cache, just as expected. In this video, we learned about using map triggers to perform some operations just before the cache transactions. In the next video, we'll have a look at the continuous query cache. In the previous video, we've studied map triggers and its concept. In this video, we'll learn about the continuous query cache mechanism. Before we begin, you should download and extract the continuous query cache.zip file and import it to your workspace. Let's take a look at the continuous query test Java class. At the top of the code, I've created a traditional cache, that is, a customer's cache, which we will fill up. After that, we'll create a filter for customers whose age is more than 50. Then, create a continuous query cache with a constructor that gets 2 arguments. The first argument is the actual cache, and the second argument is the filter. After creating the cache, the customers with an age higher than 50 will be stored in the CQC cache variable. Therefore, we will be able to access the filtered data easily without having to access the back cache. Let's try this example out. We have already prepared the run configuration that runs the continuous query test Java class. We will start 2 instances and will wait till the operation begins. We will expect the size of the continuous query cache to increase if we add a customer whose age is higher than 50. Type in C in both servers to check the number of elements in the continuous query cache. 5575 and 5575. Hence, the number of the elements is the same. Then let's add a customer whose age value is more than 50. Type in P and then 80. We then need to check the size of the continuous query cache. Type in C. From the result, we can see that the size is increased by 1. Let's add a customer again, but this time we'll enter his age as 30 and then check the size of the continuous query cache again. We will see that the size of the query cache has not increased as the age is less than 50. In this video, we learned what the continuous query cache is and how we can access filtered data instantly. That wraps up this section. In the next section, we're going to see what Coherence Extend is. In this video, we'll have a look at the functionality of Coherence Extend. Coherence Extend enables access to clustered data outside of the cluster. This feature is compatible with the following programming languages: Java, .NET, and C++. In this tutorial, we'll have a look at a real-world example. There is one Java-based Coherence cache server. We'll start a Java Extend client to fill the Coherence cache, and we'll also start a .NET Extend client to fetch a customer object to the C# application. Before we begin this example, you should download the extend.zip file and extract the Java project into a folder. After importing the project into your workspace, let's have a look at the cache configuration files that you'll see. First up, the server coherence cache config.xml file. In this configuration file, under the caching schema's element, we can see proxy schema. This proxy schema initiates a proxy service to handle incoming connection requests. We should specify a host address and port number to open a socket to handle incoming connections. In addition to this, we should also specify a serializer. You can also specify the serializer using the command line, but in this tutorial, we'll set the serializer in the cache config.xml file itself. As you can see, the pof config server.xml file is set for the Coherence cache server. Let's take a look at this file. The customer class is set as a portable object. Next, let's check the client coherence cache config.xml file. This configuration XML file will be used for the Java Extend client. In the caching scheme's element, we see the remote cache schema. And in this element, we can also see the initiator config sub-element. In this part, we configure the proxy service's IP address and port number. We also set the serializer as well. In this example, when we look at the client pof config.xml file, we can see that it is the same as the server configuration XML file. Our proxy service will be started by the default cache server. When you create a run configuration, you should set the main class as com.tangosol.net.default cache server and also choose the relevant cache configuration file. After setting these attributes, click on Run to initiate the proxy cache service. If we can see the clause, it means that the proxy service has been started successfully. After the proxy server runs, check the output logs to see if the TCP acceptor now listening clause is present. We now have a cache server that enables the proxy service. We will then start a Java Extend client. The Extend client program starts an Extend client and puts 2000 elements into the cache and then exits. The Extend client application uses the client coherence cache config.xml and pof config client.xml files. So when you are preparing a launch configuration, you have to specify them. Now let's run this program to see how it works. As you can see, the Java Extend client is connected to the server and inserts 2000 objects into the cache before it stops. This Java Extend client is not in the cluster. In fact, it is a standalone Coherence application. For example, when you print out the cluster size to the screen, you will see 1. Besides the Java Extend client, we can implement a .NET client as well as a C++ client. In this tutorial, we will look at the procedure to implement the .NET Coherence Extend client. In Microsoft Visual Studio, we created a Visual C# application. In order to add the Coherence library to our C# application, first download Oracle Coherence for the Microsoft.NET Framework from Oracle's Coherence homepage. Then, right-click on our C# project, add a reference, and then choose the coherence.dll file. And check Coherence from the References folder. Please note that our C# application is based on .NET version 3.5. Initially, in the project folder, create an XML file for the application configuration. This is the app.config file. In this file, we specify the subconfiguration files path. The cache factory config file specifies the operational configuration file. The cache config file specifies the coherence cache config file. And the POF config file specifies the portable object configuration file. After we set the file paths, we should create these files. Initially, create the extend client operation configuration file. In this file, we set the log properties and then we save it as the coherence.xml file. We now create another file where we specify the extend client cache configuration. This file is almost the same as the client coherence cache config.xml file as seen in the Java extend client. However, the class name attributes are different because of the .NET libraries. Finally, we should specify the portable object configuration file. This file is almost the same as the POF config client.xml file as seen in the Java extend portable object configuration file, but we should specify the .NET notation syntax to include the default coherence portable objects. And also, in this example, our portable object class is the customer object. We should specify the namespace and class name foremost in the class name element, and then we should specify the assembly name of our C# project. After we set the configuration files, we should specify the customer object. This customer object is similar to the Java customer object, but is written in C#. We will not go into the details of C# here. However, you need to know that this class has the readExternal and writeExternal method, because it implements the iPortableObject interface. It should also have a few fields in addition to the getters and setters method in its elements. So far, we have set the application configuration file, our portable object, and our portable object customer. Now we will run the main program. In the program.cs file, we call the coherence cluster and get the customer's cache reference into our application. After we get the cache reference, we pass this reference to the Form1 class. When the Form1 class starts, a graphical user interface box appears on the screen, and in the first field you can see a text box. After you type a customer ID in here and then press the Get button, the customer object will be fetched from the clustered cache that has been started as the Java Coherence server, and then this retrieved customer object's fields will be populated in the text boxes. Let's run the .NET Coherence Extend client. Once the program starts, type in a number between 0 and 2000. For example, let's try 754 and then click on the Get button. As you can see, the object with the key value of 754 has been fetched from the Coherence cluster in the .NET client, and then the fields of this object have been populated in the text boxes. I have put the C# application in the extend.zip file for easily importing this project into Visual Studio. We've just learned how to implement Coherence Extend clients in the Java and .NET programming languages, and completed the last tutorial of this course. I hope you found this course useful. Please don't hesitate to contact us in case you have any questions or feedback. Good luck with your future coherence endeavours, and have a nice day.